What if the metal protecting a futuristic starship didn't have to exist in a galaxy far, far away? What if engineers could create a metal that is several times stronger than high-strength steel? And yet, instead of behaving like a rigid, brittle block, it could actually deform without immediately shattering? Imagine taking one of the fundamental rules of material science. Strong things tend to be less flexible, and then breaking that rule, because that's exactly what researchers have been trying to do. And the result is a remarkable new cobalt aluminum material that has demonstrated a yield strength of around 6 gigapascals, roughly 6 to 10 times the yield strength of high-strength structural steel. But here's the part that makes this story truly strange. The material isn't simply incredibly strong. It can also undergo substantial deformation. In other words, what if the future of metal isn't just stronger metal, but metal that can take a hit, bend, deform, and keep going? And suddenly, one fiction material comes to mind: Beskar, the legendary metal of the Star Wars universe. A material famous for being extraordinarily durable and capable of withstanding things ordinary metals simply couldn't. Of course, this new alloy isn't Beskar. It can't stop lightsabers. It doesn't come from Mandalore. And nobody is about to forge a suit of armor from it and walk into battle with a jetpack. But the scientific idea behind it is fascinatingly similar, because the real challenge engineers face isn't simply, how do we make metal stronger? The real question is, how do we make something incredibly strong without making it incredibly brittle? And that question could change the future of aerospace, energy, manufacturing, and perhaps even the way we think about metals themselves. So, how did scientists pull this off? And what is actually happening inside the strange material when you try to bend it? Let's go down to the atomic level. Think about a piece of steel. It's strong, it's tough, it's relatively easy to manufacture, and it's been one of the foundations of modern civilization. Buildings, bridges, cars, machines, ships, industrial equipment. But steel isn't perfect, and engineers have spent generations trying to improve it. More strength is desirable. Less weight is desirable. More heat resistance is desirable. More durability is desirable. But there is a fundamental problem. When you push a material toward extreme strength, you often make it more difficult for that material to deform. And that can be dangerous, because imagine two materials. One is extremely strong, but brittle. The other is somewhat weaker, but can deform before it fails. Which one would you rather have supporting a critical aircraft component? The answer isn't necessarily the strongest one, because sometimes you don't want a material to simply resist deformation forever. You want it to give you a warning. You want it to absorb energy. You want it to deform rather than suddenly fracture. And this is where material scientists encounter one of the great challenges in engineering: strength versus ductility. How do you make something extremely strong without turning it into something that breaks like glass? This is where the Purdue researchers turned their attention to an unusual material called cobalt aluminum, or coal. Coal belongs to a class of materials called intermetallics. And intermetallics are fascinating. They're made from metallic elements, but their atoms arrange themselves in highly ordered structures. That unusual atomic organization can give them remarkable properties: high strength, high melting temperatures, resistance to deformation at high temperatures, resistance to creep. All of those characteristics make intermetallics extremely interesting for demanding applications. There's just one problem. Many intermetallics are notoriously brittle, and coal is a good example. Normally, if you have a material that's incredibly strong but prone to brittle fracture, you have a serious engineering problem. So the researchers asked a deceptively simple question: could you change a material's internal structure instead of simply changing what the material is made of? And that question led them somewhere very interesting. This is where the Purdue researchers turned their attention to an unusual material called cobalt aluminum, or coal. Coal belongs to a class of materials called intermetallics. And intermetallics are fascinating. They're made from metallic elements, but their atoms arrange themselves in highly ordered structures. That unusual atomic organization can give them remarkable properties: high strength, high melting temperatures, resistance to deformation at high temperatures, resistance to creep. All of those characteristics make intermetallics extremely interesting for demanding applications. There's just one problem. Many intermetallics are notoriously brittle, and coal is a good example. Normally, if you have a material that's incredibly strong but prone to brittle fracture, you have a serious engineering problem. So the researchers asked a deceptively simple question. Could you change a material's internal structure instead of simply changing what the material is made of? And that question led them somewhere very interesting. Imagine zooming inside a piece of metal. At first, it looks completely solid, but zoom in far enough, and you discover an enormous world of atoms. Those atoms form crystal structures, and those crystals aren't perfectly flawless. They contain imperfections, and one of the most important types of imperfections is called a dislocation. The name sounds like a defect, and technically it is, but here's the strange thing. Sometimes a defect is exactly what you need. Dislocations allow layers of atoms to move relative to one another, and that movement is part of what allows metals to deform plastically. So if you could somehow engineer the right number of dislocations and control how they move, could you make a normally brittle intermetallic deform instead of simply cracking? That was the challenge. And the researchers found a way to manipulate the material on a nanoscale. They introduced a huge number of dislocations into the coal during fabrication. But they also created something even more unusual, a network of amorphous interfaces. Think of these interfaces as extremely small boundaries inside the material. Unlike the surrounding crystalline regions, these boundaries don't initially have the same orderly atomic arrangement. And that difference turns out to be extremely important, because when a material begins to deform, those interfaces can actually help generate new dislocations. It's almost as if the material contains its own microscopic system for accommodating deformation. And this is where the story starts to sound less like traditional metallurgy and more like science fiction. Imagine an army of tiny robots. They're standing in perfectly organized rows. Everything is orderly. Everything is rigid. Then suddenly, the structure is pushed. Instead of the entire system collapsing, certain parts begin moving. New pathways open. The structure reorganizes. They often had to sacrifice some ductility. If they wanted more flexibility, they often sacrificed strength. But this material is challenging that conventional trade-off. And that brings us back to a certain fictional metal. In Star Wars, Beskar is one of the most famous materials in the galaxy. It's extraordinarily valuable. It's incredibly durable. And Mandalorian armor made from Beskar is portrayed as capable of surviving impacts that ordinary materials couldn't withstand. Now, obviously, real-world coal doesn't behave like Beskar. There's no evidence that it can stop a lightsaber. It doesn't possess magical properties, and it isn't some indestructible supermetal. But the reason comparison works is because both ideas revolve around something engineers have wanted for a very long time: extreme strength without catastrophic brittleness. And that is actually a much more interesting scientific problem than simply inventing something that is stronger than steel. Because stronger isn't enough. What if your supermaterial is so brittle that one tiny flaw causes catastrophic failure? What if it can't be manufactured into complicated shapes? What if it can't tolerate repeated loading? What if it works beautifully in a laboratory, but falls apart when exposed to real-world conditions? That's why this new material is so interesting. The breakthrough isn't simply the number. It's the combination of properties. Let's put that number into perspective. The researchers reported a yield strength of approximately 6 gigapascals. A gigapascal is a billion pascals. And yield strength tells us approximately how much stress a material can withstand before it begins to undergo permanent deformation. For this specially engineered coal nanolaminate, that number is enormous. Researchers describe it as approximately 6 to 10 times the yield strength of high-strength structural steel. But here's where we need to be careful. That doesn't mean you can take any random piece of this alloy, compare it with any random steel beam, and say, this is 10 times stronger. Materials aren't that simple. Strength depends on what property you're measuring, how the material is processed, its structure, its dimensions, the type of loading, and the testing conditions. The spectacular result here comes from a specially engineered nanoscale material architecture. And that's actually the more exciting part. Because the research they rediscovering a way of designing the internal architecture of a metal to produce properties that normally don't coexist, the RS aren't merely discovering a stronger ingredient. Now comes the moment that really makes this material stand out. Imagine you have an extremely strong material. You expect it to be rigid. You expect it to resist deformation. And you certainly don't expect it to tolerate substantial plastic strain. But in compression testing at room temperature, this coal system sustained about 15% plastic strain. That's remarkable because bulk coal is normally very brittle at room temperature. So why doesn't it simply crack? Because the nanoscale architecture changes the way deformation happens. Instead of allowing a crack to race through material, the engineered interfaces and dislocations provide mechanisms for the material to accommodate stress. And that raises another fascinating question. Could the real future of materials engineering be less about discovering new elements and more about learning how to arrange the atoms we already have? Think about that. The periodic table isn't changing. Cobalt isn't suddenly a new element. Aluminum isn't suddenly a new element. The breakthrough is in the architecture. The researchers are manipulating matter at scales so small that we're effectively engineering the behavior of atoms and defects inside material. And that could be a profound shift. Now imagine where a material like this could become useful. One possibility is turbine engines. Inside a gas turbine, components experience tremendous mechanical forces and extreme temperatures. A turbine blade is spinning incredibly fast, and as it spins, centrifugal forces are constantly trying to pull the material apart. Now imagine being able to build components from a material that could withstand substantially higher stresses. Could an engine spin faster? Could components become lighter? Could engineers design more efficient systems? Could future aircraft engines operate under conditions that would be too demanding for conventional materials? Those are the kind of questions researchers are beginning to investigate. The Purdue team specifically points toward potential applications in turbine blades and next-generation aero engines. And the implications go beyond aircraft. The same fundamental challenge appears in power generation energy systems, advanced manufacturing, space technology, and other environments where materials are pushed to their limits. Here's where the science gets even more interesting. This material isn't ready to replace steel everywhere tomorrow. And that's important because laboratory breakthroughs and commercial technologies are two very different things. The researchers produce their coal using a technique called magnetron sputtering deposition. Instead of simply melting a pile of metal, pouring it into a mold, and letting it cool, the process allows the material to be built from alloy vapor. That unusual, non-equilibrium manufacturing process helps create the nanoscale architecture and high density of dislocations that give material its unusual properties. But here's the challenge. Can you make it at industrial scale? Can you produce large components? Can you manufacture complicated shapes? Can the properties remain consistent throughout a large object? Can the material survive millions of cycles? Can it handle extreme temperatures? Can it be economically manufactured? Those questions still need answers. And that's why the next stage of this research could be even more important than the initial discovery. The researchers are looking at whether the same strategy can be applied to bulk coal nanocomposites and potentially to other intermetallic materials. If the concept proves broadly applicable, then the discovery becomes much bigger than one unusual alloy. It becomes a new strategy for designing metals. And that's where Marvel's vibranium provides another interesting comparison. Vibranium is fictional, but the idea behind it is strangely familiar. A material that seems to violate the normal rules. A material that can absorb extraordinary amounts of energy. A material that possesses properties far beyond ordinary metals. Real materials obviously don't behave like vibranium, but science has repeatedly shown us something remarkable. Properties that once seemed impossible can become possible when we change the structure of matter. Carbon can become diamond. Silicon can become the foundation of modern computing. Metals can be engineered at nanoscale dimensions to behave in ways their conventional forms don't. And now, we're learning how to make an intermetallic that combines extreme strength with unusual deformability. So perhaps the better question isn't, when will scientists invent vibranium? Maybe it's, how many properties that seem impossible today are simply properties we haven't learned how to engineer yet? And now, we're learning how to make an inner metallic that combines extreme strength with unusual deformability. So perhaps the better question isn't, when will scientists invent vibranium? Maybe it's, how many properties that seem impossible today are simply properties we haven't learned how to engineer yet? Because deep down, that's what this discovery is really about. It's a battle happening at a scale far smaller than anything we can see. Atoms are arranged, defects are introduced, interfaces are engineered, stress begins moving through the material, and microscopic structures respond. The final piece of metal may look completely ordinary to the naked eye, but inside, there's an elaborate architecture, and that architecture determines whether the material bends, deforms, or breaks. This is one of the most fascinating things about modern materials science. We used to think of materials largely in terms of what they were made from: steel, aluminum, titanium, copper. Now we're increasingly thinking about something different. How are the atoms arranged? Because two materials with essentially the same ingredients can behave dramatically differently if their internal structures are different. And that's exactly what this research demonstrates. Now let's imagine the researchers succeed. Imagine this type of architecture can be reproduced reliably in large components. What happens next? Could we create lighter turbine components? Could aircraft engines operate at higher rotational speeds? Could aerospace structures become stronger without simply becoming heavier? Could spacecraft use new generations of materials capable of surviving extreme mechanical environments? Could energy systems become more efficient? Could machines operate under conditions that currently demand massive amounts of material? And perhaps even more intriguingly, could we eventually design materials for specific jobs at the atomic level? Imagine telling a computer, I need a material that's extremely strong, resistant to heat, lightweight, fatigue resistant, and capable of deforming in a controlled way. Then imagine an AI system searching millions of possible atomic architectures, simulating them, manufacturing the most promising candidates, testing them, and feeding the results back into the next design. That future isn't purely science fiction. Researchers are already using computation, simulation, advanced manufacturing, and increasingly sophisticated characterization techniques to explore enormous materials design spaces. The metal of the future might not be discovered. It might be designed. And this brings us back to Mandalore. In Star Wars, Beskar isn't valuable simply because it's strong. It's valuable because it possesses a combination of properties that make it extraordinary. It's strong, it's durable, it's workable, and it enables technology that ordinary materials can't. Real-world materials science has a similar goal, not to create magic metal, but to find combinations of properties that nature doesn't conveniently give us. Strength, ductility, toughness, heat resistance, low weight, fatigue resistance, manufacturability. Sometimes those properties fight each other. The breakthrough comes when engineers discover a way to make them cooperate. And that's what makes this cobalt aluminum research so compelling. It isn't just, scientists made a stronger metal. It's, scientists found a way to make an ordinarily brittle inner metallic substantially more deformable while retaining extraordinary strength. That is a much bigger idea. For thousands of years, humans worked with metals by melting them, casting them, hammering them, and shaping them. Then we learned to control their chemistry. Then we learned to control their microscopic structures. Now we're learning to control their architecture at the nanoscale. And the further we zoom in, the stranger materials become. Maybe the next revolution won't be a new element. Maybe it won't even be a completely new alloy. Maybe it'll be a new way of arranging familiar atoms. A new interface, a new defect structure, a new phase, a new nanoscale architecture. And suddenly, ordinary materials can behave in extraordinary ways. So, are we actually getting closer to real-life Beskar? Not literally. Not yet. This coal material isn't indestructible. It isn't a lightsaber-proof metal. And it certainly isn't a fictional substance from Star Wars. But if by Beskar, we mean something slightly different, a material that combines extraordinary strength with properties that shouldn't normally coexist, then perhaps we're already beginning to glimpse that future. Because the most exciting part isn't that scientists made something 6 to 10 times stronger than structural steel. The most exciting part is that they challenge one of the assumptions we've carried about materials for generations. That extreme strength and substantial flexibility have to be enemies. What if they don't? What if the strongest materials of the future aren't simply harder? What if they're smarter? What if their internal structures can redirect stress, absorb deformation, repair pathways, and change how they respond as they're being pushed to their limits? And what if the next breakthrough doesn't come from finding a mysterious metal on another planet, but from looking deeper into the metals we already have? Because somewhere between the fictional world of Beskar, the impossible promise of vibranium, and the real atomic structures inside a laboratory-made alloy, there is a fascinating possibility. We may be entering an era where engineers don't simply build materials, they program them. And if that happens, the machines of the future may not need fictional metals from distant galaxies. They may be built from something even more remarkable, matter engineered atom by atom. And perhaps that's the closest thing to science fiction becoming reality that we could possibly ask for. Music rises. So here's the question I'd leave you with. If scientists can make a metal that's extraordinarily strong without making it extraordinarily brittle, what happens when they learn to control almost every property of a material at the atomic level? Because if this is only the beginning, we may not have seen the metal of the future yet. We may only have seen its first prototype,